I see that a few people are trickling in. Very good afternoon to all of you. For those of you who are here, I'm hoping you had a nice lunch, much like I did. And for those of you who are joining online, thanks for being here. I'd like to thank the organizers for having me speak here. And I think there probably can't be a better way to wrap this excellent conference off than by sharing a few insights through some of our recent works and some of my own independent views around the space of how human input still has a very valuable role, in my opinion, to play in this age of generative AI. And that's something that I'd like to shed some light on. I think all of us here are not strangers to the fact that we're going through some marvelous technological revolutions in recent times, right? Whether you think about this in the space of manufacturing or transportation, whether it's health or finance or education, there's just been a tremendous amount of innovation and progress in the recent past. But if you try and view this whole landscape using a historical lens, what will immediately become visible is the fact that there are high costs that have always been associated with the great advances that we've witnessed over the last century or so. Right? Allow me to walk you through that just to elaborate this point that I'm trying to make here. If I was to ask you about the energy sector, right, and walk through that historical lens of what we witnessed within the energy sector itself in the last century or so, one of the most significant innovations or inventions was the steam engine, right? And soon after the steam engine, we had turboprop engines that came up, or perhaps there were electricity turbines right before. At some point down the line, you had jet engines, right? And there's been constant innovation and inventions that have propelled possibilities in the world we live in. And this has led to an incredible amount of progress in mankind and on all kinds of different folds. When you think about industrial agriculture, we've seen that this has led to an expansion of food products. There's been a gradual decline in infectious diseases, which also means there's been a steep increase in life expectancy across the board. Now, along with all of these great benefits, and much like we've witnessed through historical times, they often come with crippling costs. And perhaps there's none more emphatic than climate change at this point in time. We've also been observing that there's an increase in extinction of species all across the globe. And we've observed that there have been a lot of negative impacts of industrial agriculture as well. And I guess we're no strangers to the casualties in war, which is quite unfortunate, but it's also something that technology has a fair bit to do with. Now, what does all of that have to do with what we're talking about today? Well, I'd argue that AI is no different from any of these powerful innovations that we've observed through the last century or so, which in each case brought a galore of benefits, but were always associated with some costs or unintended harmful consequences as a downstream effect. Now, I'd like to think of AI as this double-edged sword, which can absolutely lead to great rewards, but if used responsibly, right? And history bears many lessons to tell us why things could go down an unexpected path if you do not pay attention to that. Now, I was trying very hard not to do this, but I figured, well, let's plug it in, right? One of the examples that's extremely relevant these days that has been well captured in social media and other places, and we as scientists have also been studying this closely. We're aware of the fact that pre-trained large language models, or in general the entire space of generative AI, can be quite effective in providing certain solutions, right? If you think about article writing, or how prompts can be used, prompts from humans can be used to generate certain solutions that can then boost particular tasks, right? If it comes to writing or ideation or brainstorming, these are pretty effective solutions. But at the same time, one could also try and use exactly the same technologies and put them to some undesired, or if you consider there to be a few bad actors, they could misuse such technologies to perhaps execute cyber attacks by maybe writing phishing emails or writing malware, right? And that's perfectly possible in the world we live in right now. Allow me to walk you through a couple of examples that again pit the benefits against the potential threats. So does anyone here recognize the story I'm alluding to? This came out not too long ago. This is a satellite image that's pretending to pose as a peek into the story that I'm alluding to. Any ideas on what this is about? Feel free to speak up. Adam, right? All right, I see a few heads nodding. So, well, I'll walk you through this. So it turns out, in an arguably interesting application of using pretty simple AI, honestly, the French tax collectors spotted a lot of people in different regions of the country who were hiding the fact that they had swimming pools in their, premises, right? And what that essentially allows you to do is avoid hefty tax collections. And what they did was they used satellite imagery and uncovered almost $10 million in taxes, right? An arguably good use of technology in a democracy where you expect your citizens to comply with the laws you've laid out. Perhaps arguable. On the other hand, we've also witnessed, and quite startlingly, how unexpected consequences could be quite detrimental and put you even in life-threatening situations. I'm not going to go ahead and play this one here, but I'm guessing some of us have come across this video of how a Tesla that was driving on a freeway accidentally mistook the setting sun to be that of a signal on a traffic light, right, and just started slowing down. I don't have to paint that picture cleaner. We know on expressways, and if you're from Germany, on the German Autobahn, this could be immediately dangerous, right? And well, this headline here captures the essence quite nicely. It says, Tesla's autopilot thinks the moon is a big old traffic light in the sky. Not something you'd really like. But the big problem over here, and one that I'd like to underline, is quite often these are those edge cases that are hard to predict, right? Once you know this has occurred, it's probably quite straightforward to deal with an issue from a technical standpoint. But the difficulty here is the unknown factor, right? So these are classically called the unknown unknowns. How do you know what are the blind spots that actually exist in the machine learning models that you're building and deploying? Now, as a last example, because of the general interest in recommender systems in this space, I'll turn towards one of my own recent experiences. I think this was in November last year, right? I was probably chasing a conference deadline, and this is data from my personal Garmin, so a watch I wear, and I try to track some of the health vitals just to do better in life, right? As many of us probably do. And what you see over here, and I'll read it out to comic relief, it says your average night of sleep during the week is 5 hours, while you get an average of 7 hours on weekends. Right? As I said, I probably had a rough week. I was sleeping about 5 hours on average during Monday to Friday. I try to make up for it, slept a little longer on the weekends. Look at the next sentence though. It says, well, working toward a consistent sleep schedule, even through the weekends, can improve your overall wellness. So what Garmin's really telling me to do is continue sleeping for 5 hours on the weekend, right? So that you can see how very simple flaw in the logic can totally give you the complete opposite message. Well, luckily for me, I'm no noob and I didn't follow Garmin's advice, but you can imagine in higher stakes scenarios how that could be quite drastic. Now, when I think about AI and the space of discourse that's prominent these days, and also perhaps echoing the great works of Ben Schneiderman, who's a pioneer in the field, I think the AI narrative is a seesaw of extremes, right? We've probably all come across these kinds of exaggerated headlines, which are quite unscientific and very often clickbait-like, that either tell you that the AI technology is dazzlingly beautiful and can change everything in a flick of a hand, or that it's completely dangerous and can just bring upon destruction. So this AI narrative pits startling advances against terrifying possibilities. And I think a lot of this is reinforced by the pop culture that we consume, the books we read, the movies we watch, the games we play, right? And the question at this juncture is there an alternative? Is there a third perspective that puts this back into the balance? Or where does the reality lie and where should we focus in our efforts? And the answer to that question is this notion of human-centered AI. AI that can amplify human capabilities, empower individuals to make sure that they're at the center of the experiences as opposed to putting the technology in control, right? And this whole notion of human-centered AI has been catching up across research communities. I was quite pleased to see through the course of this conference, several speakers allude to the fact that it's important to build trustworthy AI systems and make sure that the end users are in control of the interactions. And again, I'm a big fan of the work of Ben Schneiderman, and here's a headshot to this excellent book that came out last year, which clearly shows how human input is indispensable in this space, right? As much as we have much to learn from what and how generative AI can play a prominent role in improving our lives, approaching it from a human-centered standpoint is the need of the hour. Having said that, where exactly are we at this point in time? What are the problems with present-day AI systems? When you think about that, I'd argue that the problems exist in engineering AI systems, how we tend to build them and deploy them, but they also exist in what we understand about how humans tend to interact with those systems we build, right? So I classify them as problems in the space of how they're engineered, but also problems in the space of how people tend to interact with those systems. And this is where I position my research, right? And I argue, and I think there is an indispensable need for human input to ensure that we can continue to build better AI systems, right? And when I say better, I mean trustworthy, reliable, robust, plug in all your favorite keywords, which have been acknowledged in recent times. And I think we need human-centered AI and crowd computing, which is a means to acquire human input at scale. We need to understand how human-AI interaction could unfold. We need to figure out how exactly explainability can be used in the space to push the envelope further. And within this computational role of humans, I think we can understand how AI can be supported by humans, right? So I'll dive into this by giving a few examples as we go along, but the counterpart to that is the interactional role that humans can also play. While humans are interacting with AI systems, how can you observe them and understand what you could do better, then reinforce that cycle of continuing to build better AI systems? And through the rest of the talk, I'll try and make a few points along those lines to articulate why exactly this can be done and how we can use crowd computing towards that end. Now, let's start off with the computational role that I'm trying to say humans can definitely play in this space. How can we improve the interactions that humans tend to have with AI systems from a computational perspective? Much like I like to do, I'll jump straight into an example. All of us here are quite familiar with conversational interactions, right? We've definitely interacted with the Alexas or Siris or Cortanas or whatever you think of in that space. There's so many digital assistants being widely used these days. What's equally prominent is experiences that we've had with conversational breakdowns, right? With a quick show of hands, how many of you have witnessed, heard about, or had a conversational breakdown while you were interacting with conversational agents? Yeah? Only a single person? That's interesting. I must be interacting with the wrong conversational agents. But no, I'm pretty sure you would agree that there are lots of interactions that break down quite easily. And one of the big reasons why this tends to happen is something that we've focused on in the last couple of years, and that's the role of common sense reasoning, right? We as humans tend to rely a lot on our innate common sense knowledge while we reason and interact and live our lives in a very seamless fashion. But that's not essentially what machines can be easily empowered to do, right? Because they, to the largest extent, rely on factual knowledge that exists in knowledge bases or other resources. So what if we could ideally elicit deep common sense knowledge from humans, represent it, structure it, store it, and then allow for reasoning mechanisms to operate over that, right? That's the vision we had. And now common sense knowledge, this is a drive that has been around for a little while, especially in the newer symbolic AI systems community, where people have been harping about the role that common sense knowledge can play. We've also looked at the space of knowledge acquisition, and knowledge acquisition methods till date don't really cater towards eliciting the deep tacit common sense knowledge that we as humans tend to use, right? Not simple generative knowledge that goes along the lines of, oh, a bottle has a bottle cap, a bottle can be filled with a liquid of different types, which can then be poured out, right? So those are surface level common sense knowledge tuples, if you may. But if you want to get something much deeper, and that's what tacit knowledge essentially means, you need better methods. How can we do that? Well, that's essentially where we stepped in, and we said, well, the need of the hour is to try and build a way to elicit broad tacit knowledge that can also be used in a discriminative fashion. And we built a game with a purpose called Find It Out, right? And I'd like to walk you through this in the next couple of minutes. So Find It Out is a two-player game. And for those of you who've played Guess Who earlier on at some point, or this might ring a bell, right? It's highly inspired by the game mechanics that Guess Who has. This game is, one that won a couple of awards in the recent past. We were nominated for the best paper at the web conference last year. We also have a patent pending on the technology to elicit common sense knowledge from humans. So how does this game work? Well, it's a two-player game, as I said, and as soon as the game begins, one of the players is assigned the role of an asker, and the other one's assigned the role of a replier. Let me walk you through it. Now, an asker can ask a question to the replier. Now, note that both the asker and the replier get to see a given set of cards that are exactly the same. So the game board has exactly the same set of cards. And the objective for both players is to guess the other person's main card. And the main card is displayed on top, right? What happens? So the asker gets to ask a question using a relational template that we have. You can configure this to your needs, depending on what kind of common sense knowledge you want to elicit, what the context is, and so on and so forth. And the asker here asks, is your card a carnivore? The replier can then respond with a yes, no, or a maybe, or even say that this question was unclear, in case they want the asker to rephrase it. Through such interactions and taking the response into consideration, an asker can then flip the cards that they want to eliminate based on the response they gathered. And through each turn, and this is where the effectiveness of this game comes into play, through each turn, we can create knowledge tuples that are generative, where you see an otter is a carnivore, is something that you've established. And at the same time, you've established that a hare is not a carnivore. This negative sign here implies a negation. And at the same time, by accumulating the generative tuple with this negative tuple, you have a discriminative attribute that you've identified, right? You can say that an otter is different from a carnivore because the otter, an otter is different from a hare because an otter is a carnivore while a hare is not, right? And that's the effectiveness of gathering knowledge in this way. And as the game progresses, and I recommend you to take a look at our paper because we dive very deep into this analysis. As the game progresses, we tend to create more and more tacit knowledge tuples. Let me give you an example. So in one of our games, we had these game boards, which consisted of the entities of floor, windows, bathroom, walls, ceiling, a chandelier, mirrors, and bedrooms. And we observed a few tacit knowledge tuples that were elicited. Over here, we saw that one of the questions that an asker asked was whether or not the card could be used for decoration. And now the chandelier being used for decoration is perhaps not the very first thing that you'd start thinking about or describing about a chandelier. It's probably, you talk about how it gives out some light, how it probably looks beautiful. And perhaps a nicer example is the one that follows in another game board where some of our players elicited that when you think about boots, you can also correlate that to the fact that cowboys wear boots, right? What we then did was we tried to collect all of this common sense knowledge that we gathered and tried to see whether or not they could be used in downstream AI tasks to improve the performance of models in that space. And we considered a couple of different tasks. We looked at common sense question answering. We also looked at discriminative attribute detection, right? We recruited over 100 players who played over 2,000 rounds, and this led to the creation of over 150,000 knowledge tuples. And the efficiency of this game is 10 times higher than a reference baseline of verbosity, which some of you may be familiar with. It was also a game that was created with the objective of generating common sense knowledge. And we validated the usefulness in common sense question answering task, as well as the identification of discriminative attributes. What we found when we looked at the enjoyability of the game, because that's a pretty important aspect to evaluate in games with purposes, because the scalability is proportional to whether or not people are actually experiencing it in a nice fashion. And turns out using the player experience inventory, there's also a pretty enjoyable game. So this is just a small example of how you can use human input in order to propel and progress in terms of improving the models that you can then deploy in contexts that might just have a pretty fundamental role in creating seamless interactions with AI systems, right? Common sense question answering, pretty fundamental when it comes to conversational interactions with systems. All right, now allow me to give you an example in the context of explainable AI, right? Which is a very interesting realm that I have begun to focus on in the last few years. This is at the intersection of AI and HCI. And again, I'd like to show you how you can use human input to improve the performance of AI systems. Let me walk you through this paper that we published at the web conference again last year. And over here, we wanted to look at trying to get a deeper understanding of what your image recognition models have actually learned and trying to identify their shortcomings thereof. Let me walk you back to that little anecdote of Tesla recognizing the moon, or the setting sun rather, and mistaking it to be a traffic light and slowing down, right? Now that's an unknown unknown. An unknown unknown is the type of error that your model makes, but it makes it with a high confidence, right? So either identifying the right class, but for the wrong reasons, or identifying something that's incorrect with a high level of, something that's correct with a high level of confidence, and you totally miss it, right? So it's very hard to detect what are these unknown unknowns. And here's one of our approach to try and figure out whether using human input to see what a model has learned and comparing it to what a model should have learned could reveal these blind spots that your models have. So now when I show you this particular image here and ask you, so there's a scene recognition task, right? I'm just gonna ask around and say, can any of you tell me what scene we're looking at? Yeah, absolutely. So we're looking at a kitchen, right? But look at what the models picked up. And if you look at the saliency map, we can identify that the model sort of focused on the fact that there's a ceiling and the fact that there's a chair to largely make its decision that this is a kitchen. Now, if you were to ask humans what the most salient objects or aspects of this image could have been, if you wanted to make that identification as being a kitchen, then you'd probably understand that, hey, a microwave or an oven or having a countertop or a sink are way more salient and demonstrative of the scene being a kitchen as opposed to a ceiling and a chair which can possibly exist in any room, right? And that's the sort of distinction that you can make while getting human input in order to identify blind spots in your models. I'd love for you to take a look at this paper because we've obviously dove to a much deeper extent and also showed how we can use that in a feedback loop to improve your models as a consequence. What we also did was we came up with a human computation workflow through the course of this work that allows us to easily identify which objects are being, or which concepts rather, are being fundamentally responsible for some of the classifications that the models are making. Now, this isn't the most novel thing at this point in time, but it's certainly a very useful and effective workflow in order to identify the unknown unknowns. Having said that, allow me to walk you through another example that has been accepted at IUI and will be presented in Australia in about a month from now, where we built this tool called Perspective, right? One of the classic things, and I think many of you will shake your heads when you hear this, is when you try to rely on human input, there are just a ton of biases in play, right? You're trying to gather labels from humans to train your models so that they can perform accurately in a robust setting, right? But what often happens is there's just a truckload of biases. Now, some of the biases are because of the fact that we as humans or people who are labeling data have our own experiences that we take to the task that we're providing labels in. On the left-hand side, you have an original image of a croissant, right? Now note how the croissant is only occupying a tiny little bit on the bottom left of the screen, but there's every reason why this image should be tagged as being a croissant, of being that of a croissant. But what would a labeler actually assess this as? Now, when I ask you, is this a typical image of a croissant? Can some of you put your hands up if you think, yeah, that's what a croissant would typically look like in the world? Who thinks this is a typical image? All right, we see a few hands. How many of you think it's not a typical image? Yeah, some of you see. So there's obviously a variance, right, between how people perceive typicality. Now, if I was to dive a bit deeper and ask you, hey, is that typicality based on your experience of all the croissants you've seen in the world? Some of you might say yes, some of you might say you had different kinds of criteria. But the point is, when we're labeling data, often what your models are learning are statistical patterns that exist in your data, right? All of us are familiar with that notion. So it's only fair that you provide that inclination to the humans who are labeling specific data. So what we tried to do was bring that to the fore. And we said each time we're asking people to label something, let's also gather information about how typical this particular image is within that class of objects, right? So how typical is this croissant, either with respect to all the other croissants in the data set? So you have multiple views that the users can toggle between. They can look at a random sample of similar images, right? Which is what you see here. And then you see that, hey, some of the other similar images actually do have croissants as the subject of the image. It's not just lying around somewhere. And then you can also look at what are the other visually similar images. And then you'll see that a lot of the visually similar images are coming from different classes. Some of them are about smiles, some of them are about something else, right? And that's the understanding that you can take while trying to figure out whether or not there are blind spots in your data set, whether or not there are things that are statistical patterns that are being learned, which are actually undesired, right? And this particular workflow and interface that we built is what we call perspective. And we also came up with a characterization of atypicality of images. What exactly is an atypical image and how we can quantify that and operationalize that in a context such as this to build models that are more robust in different settings, or at least ensure that humans have a better understanding while they're labeling images. At this point, you go, hey, that's nice and dandy, Ujjwal, but can you tell me more about the interactional role that humans can play? So far, I gave you a couple of examples on how you can elicit human input and use that in interesting, effective ways in downstream AI tasks. But what about interaction roles? And as different research communities aim to progress in this direction of understanding human AI interaction better, I think it's essential to be able to observe humans interacting with AI systems at a large scale, and then take learnings from that while we build the next generation of AI systems. And with crowd computing, that's essentially what we can do. We can orchestrate large-scale human-centered experiments, run randomized controlled trials and user studies to inform some of our design decisions. And that's essentially what we've been doing over the last few years. I'll give you a couple of examples. First, starting off with this collaboration we had with a few behavioral scientists, behavioral economics from the University of Göttingen in Germany, where we used the lens of the ultimatum bargaining game to try and study how dependence on decision support systems would affect the behavior of humans, right? Nowadays, we're seeing human AI decision-making all around the place in all kinds of sectors. And to the largest part, a lot of these systems have been adopted without fully understanding how humans might interact with them. What's the impact of system adoption on the society at large, right? And these were the fundamental questions we wanted to study, and we wanted to use this framework of the ultimatum bargaining game to that end. For those of you who are uninitiated, how the game works is there's a proposer and there's a responder, and there's a simple single shot setting, right? Now the proposer has an endowment. Let's imagine he has 100 Singapore dollars, and the proposer can offer a share to the responder. Now, if the responder accepts that share, they have a deal, both of them get the proportionate amount. But if the responder rejects it, both of them get nothing, right? It's a very simple single shot setting. But it's also a very effective workflow because it's essentially the same sort of basic dynamics that you would observe when humans interact with AI systems, right? Which is why it's a very effective framework to study things. I'll just give you the long story short version of it, TLDR. What we found was that the perceptions of fairness that we were measuring in a controlled experiment changed due to the introduction of an automated decision-making system. Right? So we had conditions where people were interacting with humans alone, and then we had this introduction of an algorithmic decision-making system that the proposer could use, right? And this all of a sudden changed the perceptions of fairness. But when we added a layer of explainability where the participants could understand what exactly the algorithmic decision-making system is doing, this increased the cooperation amongst players, right? Now, the reason I bring up this example and why I'm talking about this is because the effect of AI systems on human behavior, especially in economic bargaining environments, are all around us. They're extremely relevant. We've seen this, there's a surge in algorithmic pricing, right, across e-commerce platforms and other places. There's a lot happening in terms of using automation in hiring decisions because of the volume of applications that go out across different sectors. And there are also a lot of other choices that are often shoved under the carpet when it comes to what the AI is actually doing in those decision-making contexts. Now, I'd like to point out to these many promises that AI is supposedly going to take care of. And I'd say that the AI technologies do hold great promises for market organizations and the society at large, but we often fail to address two of the core assumptions underneath these things. One of the first conditions that has to hold up for AI systems to be very effective is that people should not actively avoid them, right? Imagine you create this fascinatingly effective system that can help people perform tasks very effectively, but no one uses them, right? Imagine the system's just lying there. So one of the first conditions is that people do not avoid those systems fundamentally. And the second condition is that AI systems do not systematically err in predicting human choices. To what extent are these conditions actually going to hold up in the real world though, right? That's something people haven't really looked at. And in our work that was presented at CHI last year, what we found, again, the TLDR version for you, was that humans tend to overwrite their own economic self-interest in order to avoid bargaining with AI systems. So to give you a peek into what we did over here, we had another control study where there were humans who could either interact with an AI system to strike a deal, or with another human, or with another human who had an autonomous agent that could aid them in the decision making. And what we fundamentally saw across the board was people avoided the AI system even though they knew they would lose out on some money. So they would trade off their economic self-interest just to avoid the algorithm, right? So quite startling finding, especially when you think, oh, there is so much to be gained, but that's not what happens. So a lot of us have been thinking about this age as the AI summer, right? Some have cast it as being the golden age of AI. And using the metaphor of an iceberg, I'd say that in this golden age of AI, much of the work has focused on the algorithmic lens, which I would argue is the tip of the iceberg. And there is plentiful to be explored from the human lens, right? Again, a couple of examples. You can understand how explanations should really be delivered to humans, right? At the end of the day, you can come up with explanations, but we shouldn't forget that these are eventually going to be used by humans in their decision-making context. So how do you present them? What is the modality that you could use? What's the difference between using textual snippets as explanations versus presenting the same thing using an audio format or using graphics in combination with all of that? Again, looking at a classic decision-making context where an AI system can give you some advice, we found that explanations in general have a positive effect on decision-making, but we also found a disparity across the modalities, right? It turns out that text and audio explanations are most effective in helping humans out. But we found that when you're using graphical explanations, they're pretty poor when they stand alone by themselves. They're much rather, or you would much rather use textual and audio explanations alongside those graphical explanations if you want to help users out. I'm aware that I'm probably getting closer towards where I need to start wrapping up. So let me remind you of some of the consequences of XAI. Why am I talking about this in the first place? And I'd like to do that with an example. Imagine you're driving a car, right? And I want to paint out what reliance on AI systems actually is through this example. Let's say you're all driving a car in some location, and you tend to rely on your GPS system. Now, when you have this navigation support system, what's interesting to think about is there are these contexts where you can trust your navigation support system a fair bit, and then there are contexts where you probably don't want to trust it at all. On the one hand, if you were to rely on the system absolutely, you might end up finding yourself in trouble because, well, maybe the speed limit of 60 has actually been updated, has not been updated in your navigation support system, and then you're zooming past, and all of a sudden, you get a fine. Or a disuse or a lack of reliance on the system on the other hand, where maybe the system's telling you, hey, there's a traffic up ahead, why don't you turn right? And you're saying, well, I don't believe you. And you stick around and you find yourself in a traffic jam. Now, disuse is something that you don't really want because you might lose out on some benefits, but over-reliance might also lead to some problems, right? And sometimes these problems could also be quite drastic. Not always, but the stakes vary and can be quite drastic, right? So it's this notion of trust that's at the core of all of this, trust that you're building in the systems. And one of the definitions that I personally love when operationalizing this in different contexts is that of Lee and C, who came up with it in 2004. And they say the attitude that an agent will help achieve an individual's goal in a situation that's characterized by uncertainty and vulnerability, right? So there's got to be some amount of cost associated to why you would use this system. Right? Why do I need to use an AI system? What am I losing out on? And it's in those contexts that trust manifests. And it's exactly in those contexts that we need to study this, right? And that's where human AI interaction and human AI reliance or complementary performance comes to the fore and becomes meaningful. So what we've been trying to look at in the recent past is how can we orchestrate or facilitate appropriate reliance on AI systems? What can I do to make sure people don't over-rely on a system or don't under-rely either, but rely in an appropriate fashion when the system's likely to be correct, but rely on themselves when the system's likely to be wrong. So imagine you're driving a car and in a city and everything you followed on the GPS was always right. You end up building trust in everything it's suggesting over time, right? Now imagine you take that same car and go to a little village where perhaps the live GPS data that's being transmitted to the satellites hasn't been updated in a long time. If you fail to understand how the system works, you're probably just going to trust it in a small village as well and find out that you're hitting a dead end or you're stuck in the middle of nowhere, right? Because the data hasn't been updated apparently. So that fundamental understanding of where the decision is coming from and why could help orchestrate appropriate trust or appropriate reliance, which is then, your trust translates into behavior, which is what we look at as reliance. Through a body of works, which I'll just zoom through to give you the intuition of how we've been exploring appropriate reliance, we first started off looking at, do people even understand what stated accuracy is? What if I was to take a layperson and say, hey, here's a system that performs with an accuracy of 75%? Good luck, right? How do people calibrate this? There's obviously a numeracy scale that all of us differ on, especially when you consider the fact that there are thousands and millions of lay people who are affected by the introduction and adoption of AI systems in the real world. It's important to understand what exactly this would mean. Is there a role that analogies can play over here? I found this idea fascinating back in the day when I was reading this book about how analogy is the fuel and fire for all cognition. I started wondering, shouldn't we use analogies to explain things to each other when you're dealing with complexities? We as educators tend to do this all the time during our lectures and classes, right? Where you just pull up analogies out of your hat to try and explain something that someone probably does not understand fully. So what is an analogy? An analogy is a structural mapping of a target domain that you would like to clarify onto a domain that your recipient probably understands well, right? So if I'm explaining some complex equation in math, I'd probably draw an analogy to something the students probably learned in the year before, right? Say that, oh, it's just like this, but this is the difference. Can I do that? Can I say, hey, this system's 75% accurate, which is about as reliable as the AstraZeneca vaccine, because hey, people are probably familiar with how accurate that is. With Dima standing up, I think I'm running out of time. I have some time? All right. We also then started saying, can we create analogies and use analogies as a part of explanations? Because imagine you have explanations, right? And these days we have a lot of algorithmic methods that can lead to explanations, which you then present to the end user. And at that point, you're essentially saying, hey, good luck. Here's a Lime heat map or a SHAP rendering of a saliency map. Good luck, right? I think we need to go a step further, because you want your end users to actually find these explanations and make sense out of them. Can you use analogies at that level? Let me walk you through an example. So let's say in this context of trying to explain a complex medical diagnosis to a layperson or a patient, you have this concept level explanation that has been extracted. And the concept level explanation goes with cribriform and fused glands in the needle core biopsy from the prostate. This is diagnosed as being the adenocarcinoma of the prostate. All kinds of Greek and Latin to most of us here, right? Now, what exactly can an end user make out of this? If you could go a step further and try to draw an analogy and say, hey, cribriform and fused glands in needle core biopsy is definitely a sign of prostate cancer, much like recognizing a unicorn due to a horn on its head, right? So at that point, the consumer probably understands that, hey, I don't know what cribriform and fused glands are, but I do understand that this is a definite identifier of the fact that this is indicative of prostate cancer, right? To paint that picture clearer with another analogy, so an analogy on the whole analogy, is imagine you have experts, right? Experts are empowered with some of the tools, maybe their domain knowledge. Maybe these experts aren't people who really need such analogies to make full sense of the explanations that exist these days. Because an expert knows how to steer the ship, can get on the ship, steer it, and get across the river, and then eventually get to the abbeys of appropriate trust and reliance. But what about lay people who probably don't have the expert knowledge to navigate a ship and get across the river? All they have are a pair of shoes, right? So can we build a bridge that uses analogical inference so that these lay people can actually get across that bridge and reach those shores of appropriate reliance and trust? So that's essentially what we're getting at. And in that exploration of how we can build appropriate reliance, we've looked at a series of things that range from intelligent systems, how exactly you use metaphors and anthropomorphism, conversational AI, and most recently, and I'll end with this last one, we also looked at how cognitive biases can play a role in how individuals interact with AI systems. And all these explorations have been done by using large-scale human-centered experiments, which are extremely effective in trying to understand key aspects of human-AI interaction and what we can take away. I must say that all of this work was largely done thanks to some of the exceptional PhD students and postdocs that I have the pleasure of working with in my group, and several collaborators outside. I'll close with this statement that I'd like you to take home. Crowd computing offers a promising means to overcome fundamental challenges in both computation and interaction, and this can allow us to herald a new generation of human-centered AI systems. Thank you very much for listening. I'd love to hear some questions now.